Right. And also, it just seems like maybe what I see is that uh half of like maybe like one third of us here are um do not have too much of do not have very deep machine learning, do not have like too much of machine learning background, that's especially to do with diffusion model. And then and some have and also some are also not with uh, transformers. Do want to say this is a paper reading group that we have um, done have been meeting for some time, and then have gone through uh, different foundational papers for transformers and diffusion models. And so I'm going to be share links in a moment about our previous workshops. So if you wanted to ever catch up, but still with this, when we are before we are like diving deep right away, maybe Kobe can give a like a very very high level on like transformers and diffusion model. Um,
Yeah, sure. Okay, so hi everyone, welcome. Today
mhm.
we'll discuss the paper which is called Scalable Diffusion Models with Transformers. So before doing that, we can give a very brief introduction on what is diffusion models. I think I have a slide on that. So diffusion models is actually very simple. We have a forward process which basically add noise to real data. Basically, you can think about we have a clean image and then we try to corrupt it until it has no information left. And the reverse process simply we just learn to undo the noise from the last step until we got to the clean image. And so typically the model is trained to predict how much noise is added at each step. And in the inference time, we start with the last step, like some form of a Gaussian noise, and then we gradually, step by step, we move towards the clean image. So it's very simple. Diffusion models try to generate data by gradually removing noise. And transformer is another architecture which is very famous in NLP, the paper. Attention is all you need. So at the core, what transformer does is basically we are trying to, so let's say I have a sentence, this word answered yes. So the idea is that we break this sentence into a bunch of tokens, like a bunch of words. Like we start with this word this, we start with this word work. And so we typically have a starting embedding for each of the word. And the idea is to use attention. So let's say I'm the word this, and the idea is that the word that is after this is going to pass some information to the embedding of the word this. And so basically the idea for transformer is to we want to learn a good embedding for each word such that the embedding of this word actually contains some sort of information from other words. For example, what is the part of speech, or maybe what are the semantic meaning of other words. So basically, after learning a good embedding for each of the token, typically transformers are good to predict what is the next word, like what may come after the word unit. And so yeah, so that's the basics of transformer. So any questions here?
Yeah, if I were to also quickly give a little bit connection to how is that connected to even broader concepts, is that in uh, the in the sorry in the AI, we have the generative AI or uh, the traditional kind of discriminative AI, where discriminative AI is for predicting things and then for uh, categorizing things, but mostly to do with structured data. And then and it's really just started from 2016 and it really got popular in 2 years since ChatGPT. We have the generative AI, and the generative AI really have like two folds. Most of it is a transformer architecture, um, which is autoencoder based architecture that uh, that works the best with language generation. And then we also have the image generation type of model, which architecture, which is diffusion models. And then so both of them formulate this type of model called generative AI. And then because it's generative AI, it can work with uh, uh, generative tasks, and so it can generate things where it's didn't see the exact pattern before, and then and can and have and can it is also uh, can learn patterns much faster. So because it also can be called as foundation model, so that it can be really helpful for being the foundation of building different other type of models. And then, but if you're actually talking about um, the 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 joint between diffusion model and transformers, that's kind of there are some different architecture that we can be talking into, uh, like the diffusion transformers, vision transformers, different ones. We will be talking about how the the most common one today, um, diffusion transformers, and then yeah, so when transformers working with language combined with the diffusion model working with image generation, now we can actually have a model that understands image, understanding text at the same time and generating image with text and with image. And then from this, we can also do videos to do anything else that is kind of in between text and images. Um, the, uh, so it's kind of became the most popular uh, image video generation model space architecture of today. All right. So that's kind of some very basic knowledge gets to hear today. And then feel free to add more or point out things to correct me for Kobe, Blush, and uh, uh, Utkarsh, Tristan, and other friends.
Yeah, yeah. If I said something wrong, you can just interrupt me. Yeah.
Yes. Mhm. Uh, yes. And uh, uh, also, just wanted to say, for we for those of us who wanted to learn more about what really this community is about, we will talk about it in 15 minutes each, and then and we also have a online little community where we uh, build some diffusion model related projects together and talk about the paper we reading and share the paper we've been reading. Then it's oh, Kobe, if you can enable us to chat, then I will be able to share that with the information with us.
Just one second.
Mhm.
Yeah, I think I send a message.
Cool. Feel free to go ahead.
Okay, so yeah, so basically, units. If you don't know unit basically you can think about is a auto encoder. Basically, we have an image, let's say 256 by 256 pixels, and then we sort of try to encode it into some form of like very small dimension, let's say 16 by 16, and then we try to go upwards such that we try to reconstruct the clean image from like the bottom one. So yeah, unit is for you can use that for image classification if you want to, because it's based on CNN. So what's CNN is a convolutional neural network. So that's traditionally used to classify images into some class. So basically, it's a way. So we have a big image, and then we sort of try to first bring down the dimension, and then we try to pass it, and then we try to sort of concatenate everything into a big vector, and then we pass that big vector into some neural net, and then hopefully it will generate the prediction. So this work is try to apply transformer to the diffusion problem because yeah, the diffusion models they typically use convolutional units. And yeah, so the answer is actually yes. So diffusion models can use transformer backbones instead of units. So let's give some brief preliminaries. So we talk about the diffusion stuff. And so training basically typically we try to predict the noise that is added to a corrupted image. And the loss function is very simple because during training we know how much noise is added. So we simply just do the mean square error between predicted and true noise. And for sampling, we start from the pure noise, a pure Gaussian noise image, and we iteratively denoise until we arrive at a clean image. And this will produce a new image from scratch. Now, a little bit more. So, if we want our images to sort of follow some form of a guidance, like for example, class labels. So, let's say I may have 10 classes like cars, birds, whatever class you can think of. So, in this case, we want to train our model with and without conditioning. So, this conditioning can simply be a class label. And at sampling time, we may want to amplify the conditioning signal. And so classifier free guidance basically is a way to improve your generated sample such that you sort of follow the prompt. And we'll
The,
discuss how this can work in the model. But yeah,
yes,
any questions?
the sampling process is when we
Yeah.
generate the final result, or the result when we are giving it a text prompt,
Yes.
um, in inferencing time.
Yes.
And, and then feel free to interrupt if to ask the questions, even if it's very basic. If it's too irrelevant, we'll tell you. Yes.
Oh,
Okay. Mhm. Mhm.
so now latent diffusion model. So typically the early days of diffusion models, we work in pixel space, which means that if your image is 256 by 256, we have to work on each single pixel kind of. Now what latent diffusion does is we first train an autoencoder, maybe uses EN. In this way, basically we can compress our images into a less what do you call it, less dimension. Like we compress it into maybe 16 by 16. And so in this way, we can perform diffusion in a very smaller space, and you can save lots of compute and with similar image quality. And so what this means that you when you do the diffusion step, you have the corrupted sample like 16 by 16. We pass it towards the diffusion step, and then you get a 16 by 16 clean image, and then you pass through your decoder to get a sort of a bigger image, like maybe 256 by 256. And the training happens already latent space in the diffusion.
Okay, um, so latent diffusion, mm, can you compare the latent diffusion model with the traditional diffusion model?
Yeah, just in the smaller
There,
space.
mhm.
We have to first compress the original image into like maybe 16 by 16, because in this way you can save compute.
Mhm.
And then we first train a compressor, basically.
Mhm. Okay.
Any questions?
I just had one question.
Yes.
Um, it it is related to latent diffusion compression. So is it different than the traditional convolutional pattern where we had, those metrics where we had to specify strides, all those things?
Yeah, it's typically a convolutional neural network. Yeah.
Okay. And how we are like storing the positional information in this case?
What do you mean positional information?
Um, so I think we are reducing the size as well, right? You said like
Yes.
16 to
Yes.
16.
Yeah. And
So how?
yeah,
Mhm.
basically in the diffusion, so we will give it a Gaussian like 16 by 16, and then it pass through the diffusion process, and then afterwards we'll get a 16 by 16 sort of a clean image, and then we pass it to the decoder to get a original size like 256 by 256, basically.
Okay.
Yeah.
When you say like mm, trying to uh, preserve this location information,
Yeah.
you're saying the when the original image get passed to the 16, it get become the compressed to 16 by 16, it loses a lot of original details. Uh, so how do we
Yeah. Yeah.
kind of have them back? Yeah. I do you know about the Kobe?
I think because image generation, we are not trying to copy the original
Right.
image. I
Yeah.
don't think the positional information matters though, because
Okay.
we're trying to generate new images, so it doesn't have to follow the original image, I think.
Okay. Okay.
Yeah.
So I think it like more of like shrink and enlarge type of thing.
Yeah.
Okay.
Mm, it's shrink, but then it's when it's go large, it's going to a almost it start to make change out of it.
Yeah. Just try
Okay.
to enlarge it, sort of, I guess.
But is this convolution or is this like a VAE?
This is
Because VAE,
convolution. This is convolution, actually.
uh-huh. But VAE like serves the same function, right?
Yes,
It's
but
a
convolution,
visual autoencoder.
yeah, convolution is better usually because you can just do sort of image to image stuff. But I
But
think
Wait,
yeah,
wait 1 second. Blas, I might be misremembering. Does VAE use convolutions in it? I thought it did.
oh no, I don't think it uses convolution, but it does the same thing, right? It compresses a big
yeah,
image into a
Yeah.
small image, and it's called a visual autoencoder. So I know VAE is used in certain models, but I don't know if it's used in this particular context.
yeah,
Okay.
VAE, yeah, you can use VAE or convolution, sort of.
Mhm. You,
I might be confused. Is it in a like vision transformers where we add like sort of positional encodings in
Yeah,
front of?
positional
Okay.
encoding. Yeah, we'll explain that. So that one is basically we divide the images into a bunch of patches. That's actually
Okay.
not
Okay.
position of the objects.
Okay. Okay. Now I got it. Okay.
so well, okay, great. If you're actually also going to that today.
Yeah, okay.
Mhm.
So yeah, basically, if there are multiple subjects to generate image, we just do one pass. Like we go through from one pass to the from the noise to the clean image, and then it's supposed to contain everything, typically. Yeah. And the attention part is part of the training is not part of generation, usually.
Kobe, we have a question in chat.
Yeah, I just answered. I said you just
Sorry. Okay.
and then attention typically happens in the training, and then we don't do attention in the inference time. And we'll talk about this in the next few slides. So let's give a few key terms before we begin the details. So GFlops, this is basically giga floating point operation. So basically this describes how much the computation the model uses in terms of billions of floating point operations. Like basically you can think about how many pluses, multiplication, division, whatever. And we just simply count how many of them for a particular model. And to evaluate the model, an image generation model, typically there are two ways. The first way is the FID, which is the free shed inception distance. This basically measures how close the generated images are to real images. So it's kind of, we try to, like, let's say I have 10 generated images, and sort of I put them in an array, and then I have 10 real images, and then I try to compare the two arrays in terms of some sort of a distribution, and we hope that the two distribution are matching. And the second one is the inception score, which this is very simple. It just measures the image quality and diversity. So basically, if I want a model to maybe generate 10 images of a car, you probably want the 10 cars to be different instead of the same car every time. So here, higher is better. And so so why do you want to use transformers? Because transformers, they are good at learning token representations. Maybe the token can be a word. Here we want to token to represent a image patch. And self-attention, we can let token share information globally. And this makes transformer effective for modeling complex relationships. And so what is DIT? So diffusion transformer. So the core idea is that, so suppose I have a image like maybe 4 by 4 pixels, like each square represent a pixel. And here P is the square, P is the size of a patch, let's say maybe 1. And so you know that the length of the DiT block will be I divided by P, and then we square this thing. And the hidden dimension is basically the dimension for your neural net that we'll talk about later. But basically, it's a way to divide the images into a bunch of squares, and then we line up the square into a big vector, sort of. And typically, a smaller patch size will result in a longer sequence length and more floating point operations. And so for now, each square is basically maybe 1 by 1 or 2 by 2 or 4 by 4 pixels. You can think about it as a sub-image, basically. That's the pre-processing part. And so how do we go, from latent to tokens? So the input of the DiT is typically what do we get? We first compress through a autoencoder, maybe VAE, maybe CNN. Let's say it's 32 by 32 by 4. Maybe we can have 4 channels or 3 channels, as much as we want. And we patchify, we split Z into P times P patches. And each patch is linearly embedded into a token dimension D. And so the total number of tokens is I divided by P squares, and smaller P will give us more tokens and higher floating point operations. And patch size has little effect on parameter count. So basically, after we got a square, let's say 4 by 4 pixels, we sort of concatenate them into a vector of 16 values, and then we pass that vector into some form of a neural net, and then you will return maybe a larger vector like size 256, and that will sort of be our initial token embedding, basically. Any questions here?
Just quick question, just for my understanding. So when you say tokens,
Yeah.
are you also including like n-grams there?
Sorry, what, Graham?
N-grams. So
Uh,
whenever we, yeah,
the text, we can also include the text token as well. Yes.
okay.
But for simplicity, we assume we only have the images. And we are
Okay. So this function is valid for unigrams in that case.
this is just for dividing images into patches, and then we'll talk about the text part later.
Okay, sorry.
Sorry,
The other question, what does this Z represent?
sorry, what does what represent?
Z in the latest slide.
C?
Z.
Uh,
Yeah, map Z,
wait,
split Z,
uh,
or Z.
oh, D.
Pass point.
Z,
Pass
the first
point.
one.
Which one?
A feature map Z.
Feature. Oh, this one. Z,
Yeah.
just say, it's a way to, it's a compressed image. Like we compress from 256 by 256 by 3 channels into a smaller dimension, basically.
Okay, so we are referring the compressed image as this alphabet,
Yeah, the Z is basically the thing, the I times I.
this whole matrix.
Yeah.
Okay, understood. Thanks, Yoga.
Please. Any other questions? So now we can talk about the overview of this. So after Patchify, we just apply the tokens, we send them into a transformer block. And each transformer block is a standard VIT. It's basically it's a transformer that is working on images. And so the diffusion model.
Actually, if you can just can you actually dive into a tiny bit of VIT and
Yeah,
then
sure.
architecture?
Yeah, so typically, where's this? Typically a VIT simply means that we only have the images. So what VIT does, VIT is not for diffusion, if you remember. So VIT, typically what VIT does is you can use that for like classification stuff. So what VIT does is we have what is this? Yeah, VIT basically, so after we have these tokens, and then we pass this through a transformer because like each square you can think about is a word, it's a token. and then we pass this to a transformer, and then you will sort of predict like after I have the embeddings for every token, I can do some form of a classification. Like maybe I concatenate every token into a huge vector, and then I pass that vector into a neural net, and then you will predict maybe what is the class of the image. Yeah, so VIT is not for image generation. It's typically for prediction purposes, just like CNN does. Yeah. So it's basically transformer with patches instead of actual word tokens.
Trade. Okay.
Yeah. Cool.
Okay.
Cool.
And
Yeah.
so I guess that it's really good for image classification.
Yes.
And then and okay, so when you okay, let's continue. Let's continue. So the how it's actually a part of.
Yeah. So we'll talk about this in the
So each
diagram. Yeah.
okay, so each block, so
Let-
each patch or each block within the kind of the DIT,
let-
it has a VIT.
yeah. And VIT is a transformer basically. Yeah.
Mhm.
And yeah, so typically, yeah, diffusion models, we also need time steps for time step areas, like 900 or maybe 100, and some class labels, C, or maybe some text. And so what is the question? The question is how do we inject these two things into our neural network? And so there are a bunch of ways to do this, but we can look at the diagram first. So this is the diffusion transformer stuff. So the DIT block. So the DIT block is this is the there's the rectangle representing the DIT block. So if we compare that to an actual transformer, so if you remember what transformer does is we start with a bunch of tokens. We add positional embedding and then we do the attention. So attention is the way we starting from the first word, the other words will pass on some information to the first word. And so what happens in the here is that we start with the input tokens, basically typically just the patches of the image. And then the layer norm is just basically it's like given a vector, we try to normalize it such that the values will follow a normal 0, 1 distribution. And the scale and shift is that we want to shift the normal distribution a little bit. And how do we shift this? So we basically apply the gamma and beta terms. So so what is so normalization is basically x minus mu divided by sigma. So basically, given a vector x, we subtract the mean of the everything, and then we divide it by the standard deviation. And layer and this normalization, this adaptive normalization is we want to shift the normal distribution and also to sort of either expand or maybe contract it. So to do this, we simply multiply this resulting vector x by some value gamma, which is a scalar, and we shift it by some value beta. And how do we get the values of alpha and beta? So what this paper does is they have a neural network. So suppose I have a time step t, like maybe 15. So this 15 will first pass through a neural network to get some embedding. And then class will also have an embedding. Let's say I have a class, let's say I have 10 classes, and then I'm in class 2, maybe a dog, let's say it's the second class. and typically just a vector of size 10, and then the second value will be 1. And then so we kind of concatenate these two vectors into one vector, and then we pass this through a neural network, and then the neural network will sort of predict the value gamma and predict the value beta.
So the idea is that the timestamp, so that the reason we're passing the timestamp is so that the neural network knows
Yeah.
when the training is happening and what timestamp is at
Yes.
during the training.
Yeah.
And okay, and then the class,
Yeah, and then class
yeah,
C can also use text as well. It doesn't have to be a
yeah.
label.
The reason it's called conditioning embedding is because those are passing as kind of conditions to
Yeah.
the image generation tasks.
Yeah, just the extra input because original diffusion, we typically don't have this too.
Yeah. It's
And,
Uh,
okay.
I have a small question. So since they are the conditional like inputs, if we don't like add these input, then what will happen?
If you don't add this tool, your model may not follow your prompt. Like if I asked you to generate a dog, maybe it will not be a dog, but kind of.
Yeah, because like the model use it's only just have the inputting prompt, but it doesn't have the class. Well, the class is recognized throughout the training process.
Yeah, the class can also be text as well. It doesn't have to be like 0, 1 or something. It can be a text like a dog, maybe.
So
Got
the
it.
conditioning embedding is kind of at each step, each round of or each steps of the training or something. So we can we can get the new class again.
Yeah, no. So the class is passed to to each step of the generation, basically just to make sure that in each step I follow what is supposed to be in the text
Oh, okay, okay,
or
okay,
what
okay.
is
Okay.
happened next.
What's
Okay.
happened to be in the text? The text can be from the it's provided by the training data.
Yeah, text in the data, yes.
Okay, okay, okay.
So that's
Okay. So if we don't have this, it's just made lost
yeah,
on the what's the training data want or what's the user want it's
yeah,
throughout.
kind of.
Mhm.
And then yeah, time step T they just find to be useful for generation. And so yeah, so that's the scale and shift stuff. And then after we do the scale and shift, we do the multi-head attention. So basically, imagine we have a bunch of tokens, and then the other tokens will try to pass some information to the tokens. And now they have another one, the scale operation here. That's what they add, another alpha one, which is so they find this to be somehow useful, which is basically after we pass through the previous step, the previous layer norm stuff, they find it helpful to pass it multiply it by alpha and then plus x again. And so basically, yeah. So this is sort of it's like another scaling term that they find out to be kind of useful because when they try to do it without it, the quality is not that good. I think what is
What is how do we get the alpha?
alpha is another neural network. It's just like because we remember that the H the we pass this two to a neural network and then you produce gamma and beta. And in this case they will produce alpha as well. And then so alpha will multiply by this.
Oh.
So we multiply the whole thing by another alpha.
Okay, it's hard to explain what's this alpha really do.
You just scaling the thing, but they find it to be useful for some reason.
Okay,
And it's hard to justify it.
sure.
Yeah.
Okay.
And they add X again, which is quite interesting.
And what is X again?
X
It's
is
an
the
input token. We
input.
can so it's kind of like yeah, adding back a kind of skip connect.
Yeah, skip connection, basically.
I guess
And so
this is where
Just looking.
maybe this may be a pre answer to previous question that Utkash was talking about. It's like how do you preserve the location information
yes,
where you because you add an X even though you are um, downsample you are making it smaller
yes.
you still add an X And
Yeah.
then the input token, also just want to say, like, um, sorry, I misremember part, but is that throughout each run of this, are we actually getting a smaller and smaller image?
No, we operate in the latent space, like
No,
30.
we only operate in the living space. Oh, okay. All right. So that's not really actually solving what Newtcache was talking about. That's okay. So, so we kind of the latent space get us the input token,
Yeah, we get the token from the latent space.
and then it's already a smaller image.
That's why it's only image. Yes.
And then the smaller image, then we make the smaller image, we break down the smaller image to be just a
Patches.
smaller images that's made of that image
Yes.
that's patchify.
Yeah.
As in the patchify becomes the input token.
Yes.
And
Yeah.
then it's just like like and then that each input token is actually just a section of the image now.
Yes.
Uh,
Basically.
okay.
Yeah. So yeah, after scaling, we do another layer node, we do another round of things, and then we have a neural network here that's it sort of stands in the middle. And so this defines one of the transformer blocks. So this is actually a VIT block, you can think of it. This is the VIT stuff. Although they name it to be DiT, but it's actually VIT.
Okay.
Yeah,
This looks really like a just
just
like a transformer.
it's basically the transformer. You can see it's pretty much the same without the right half, just the left half. So
The encoder.
yes,
Then,
so
well, which part is the DIT?
which part is DIT? Is because this first of all is noise related. First of all, it predicts the noise. So in in the VIT, we typically just pass it through some other net to network to do the prediction. However, here we are actually generating the noise, like how much noise is contained in the image. And then because we are sort of in the reverse process, let's say we are in step 999, and then basically we get how much noise is in there, and then we subtract the noise to go to step 998, basically.
So when so so when we are getting the noise, so we fit in um a good image, and then we have some sort of text prompt we want to change to be another image.
Yeah, so this is
That
the
that that's a whole thing that we're training it for, right?
yeah.
And then we noise it. We get the noise latent. It's already very noisy,
Yes.
and and then then we get a uh then we get to the very top block of noise that is just even more noisy.
No. So because in the reverse process, remember we are trying to we're trying to denoise this image.
Denoise, okay, denoises.
So we
Okay,
want to figure out how much noise was added at that step. And then so we want to subtract this thing basically.
okay. That's great. That's great.
Yeah.
And then so when we are denoising it, we also pass in the text condition
Yes.
that it knows what it should look like.
Kind of. And yeah, so this sigma is just some standard deviation. It's for sampling purposes. If you don't want your model to be deterministic, you can do some form of sampling. Because this is kind of mean, this kind of standard deviation. But typically you don't need to the second part. You just need the noise. And so they experimented a bunch of options. So they claim that this option is the best. And you can do some other stuff. So for example, instead of trying to do this all kinds of complex like gamma, beta, alpha, why not just treat the text as also tokens? So remember that this Patchify is just a bunch of tokens. So I can just put a text token at the end. You don't
The
technically
text token is the kind of the text prompt.
yeah, the text prompt. I can simply just give you the transformer and then I have the embedding for each text token, and then I just put the token at the end. And then I just give everything to the DIT, including image and also the text. So the DIT simply just does not distinguish between the two tokens, just treat it as a big sequence of tokens. So that is the in context conditioning.
I find it to be very fascinating and also hard. Also wanted to understand is that the text token and then the image token they constructed so differently.
Yes.
And then if you just mix them, how will the model just understand both very well?
Well, probably you need something called clip. So if you remember what is clip. So typically clip, what clip it does is, so we might need to do some pre-training stuff.
But okay, not this one.
Let's try this. Yeah, this is one. So if you remember, we talked about clip a few weeks ago. So what clip does is try to, so we have the text encoder, let's say a transformer. We have the image encoder, let's say a CNN. So we make sure that for each pair of text, so T1 text correspond to image 1, text 2 correspond to image 2. We want to make sure that the two vectors kind of the similarity are good. Like I1 times T1, it should be a big value. Like the diagonal needs to be very large. Just to make sure that the embedding of text and the embedding of images, they live in the same space. So that when we mix them, it's not going to confuse the model, sort of.
I see, I see, I see, I see, I see. Okay, so it's in this case that's recognized
Yeah.
technically. Okay.
And the third way, which they do, is cross attention. So cross attention, so we treat the text tokens separately. So let's say I have the text, the diffusion transformer. So this will be 3 tokens, and then your images may be 100 tokens. And then the idea is that the 3 tokens will try to pass some information to the 100 tokens. So that's cross attention. Self attention, basically, we only do it within maybe only within the image token. And so cross attention basically means that the information is passed through from the text token to the image token. And that's another way to sort of inject the text information into it, kind of. And yeah, they find that the first way works the best, which is the adaptive layer norm 0. And another thing is that they find that if we initialize the alpha H to sort of output 0 initially, and they find that this thing somehow improve the training without mathematical justification. But yeah, so that's what they denote as layer norm 0. Yeah, just initialize this thing to be 0. Yeah. So this means that your transformer will not do anything in the beginning, just X. It's not doing anything.
Oh man.
Yeah.
Like there's so many things that people are doing, but they don't follow down.
Yeah, they don't justify it, but somehow they works.
They're justified. Okay, okay. Maybe they
I,
don't talk
I,
about
I think the multiplier will also try to concentrate. So let's say if you have like normal distribution,
Yes.
so it will try to concentrate, the values which have like more probability into the center part.
Mm.
So yeah, I think that is one explanation that I see from the statistical point of view.
Mm.
When you say concentration, can you explain why that's the case?
Yeah, so if you have like some smaller values, so the multiplication of to that value will be smaller. But if you have like a higher value, so consider a normal distribution, in the center you have like a higher
Oh,
value of y, right?
yeah.
So it will try to concentrate in the middle.
Oh, okay, okay, okay. Make it the smaller number smaller, make the bigger number
Yeah,
bigger.
similar to a theorem where we do a mean of mean.
Mm. Okay. Thank you, thank you.
Cool. So yeah, thank you. So now we can do the other stuff. So basically, DiT is just a bunch of transformer stuff, and each block operated hidden dimension size D. So basically, this is the size of the token. And following the VIT practice, the ND and number of potential heads are scaled together. And so they have 4 models: DIT-S, DIT base, large, and extra large. So they claim these models span a wide compute range. They don't say how they calculate this number, but basically the larger the number, basically kind of the larger the model size, kind of. And so where's the table? So the table is, so the small model has 12 layers of transformer blocks. So each transformer block is the square. The rectangle is one of this, the transformer stuff. And so the smaller model has 12, the base has 12, the large has 24, and extra large has 28. And hidden dimension, the smaller model has 384, and then XL they have 1100. And the GFlops increases as we go from S to XL. So basically just the model size. Everything else stay the same. And so yeah, so basically, so finally the last layer is just some other layer norm. And so basically, so at the end of this thing, we have the wait. So at the end, we have like 32 by 32 by 4. So we will basically pass this to the decoder, and then you will get the normal image, like 256 by 256 by 3. So yeah, that's how you convert to the original size. And the outputs will be correspond to the noise and the variance, basically. And tokens are rearranged to recover the original spatial layouts, basically. Because we rearrange the tokens and as we have the image, basically. So the decoding thing, because what we have is because we have to go from the size D. So remember that we have this. So we kind of converted each token to a size like 384 dimension, and then sort of we have to convert it backwards to get back the image, kind of. So we just go backwards. We go back from the token like 384 by into the square that we want, like maybe 2 pixel by 2 pixel, and some channels, and then we reassemble it into the original image. That is the noise, sort of the noise, because the noise must have the same size as the noisy image, kind of. Oh. So what happens next? So the key points here, to summarize, we first patchify input latent vector into tokens. We pass the tokens into a bunch of transformer blocks, and we inject conditioning from time step and class label or text. And we have introduced 3 ways for introducing the conditioning stuff. And adaLN, the adaptive layer norm 0 achieved the best performance. And so now finally we can talk about experiments. So the model names are the size plus the patch size. For example, 2 means that each patch is 2 pixels. And we train the DiT model on the ImageNet. Basically, this is a very large database of images and labels. And we train on 256 by 256. Though this actually requires 2 models. So one model we train on 256 by 256, and then we train another model on 512. And we use the standard normalize, the optimizer and batch size. And data augmentation, this is a way to enlarge your data set. Let's say I have a car, and then I sort of flip the car to the left side so that I have more data artificially. And they have the exponential moving average. So this is a way you can keep a copy of your model, except the copy actually moves very slowly. And so this doesn't impact training, just you have a second copy of your model. And you can, maybe this is good for debugging purposes, but it's not part of the training. And they use the same hyperparameter. They do not tune the hyperparameter. They just use values that seems to be good. And so they have a pre-trained VAE. They use a VAE from Stable Diffusion, and images are encoded into latent space before diffusion. And diffusion is performed in the latent space, as we said earlier. And the generated latents are decoded back to images using the VAE decoder. And diffusion, they follow the ADM. ADM is just a unit that is in the pixel space. So the 1,000 diffusion synapse as usual. and linear schedule for the alpha and beta stuff. That is in the DDPM paper, and then standard timestamp and label embeddings. And so what they are trying to study, they want to study different kind of designs, and they want to study the scaling behavior. And so they focus on three questions: which conditioning mechanism work the best? How do model size and patch size affect performance? And what role does the GFlops play? Like how many floating point operation? And the generation metric is FID 50K. So remember that this is a way to compare your generated image to the real image, and you hope that they are sort of closer. The distributions are closer, and lower is better. And so the first experiment, they train a XL large, which is the largest model, on a patch size of 2, which four different conditioning blocks: in class conditioning, cross attention, layer norms, and layer norm 0. And actually they find that the last two models have the smallest number of operations. And we measure the FIDs throughout training, and the goal is to isolate the effect of conditioning design. So what they find that the conditioning, the layer norm 0 achieved the lowest FID at all training stages. And they find that at 400K steps, this is actually as nearly 2 times better FID than in context conditioning, and it's better than cross attention with less compute. And initialization methods, they find that adaLN-Zero outperform the vanilla adaptive normalization 0. And so they decide that all the remaining experiment will use these variants. And so they have some examples. Let's look at the paper examples. And so this is the examples that they gave. So if we zoom in a little bit, so what they claim is that the increasing the transformer size basically increase the embedding size, and also decreasing the patch size, you can see that the images are more realistic, basically. And so for example, the dog.
When they decrease the patch size.
Yes.
Mm.
So basically, each image like a patch maybe 2 by 2 instead of 4 by 4 pixels. So basically, we divide the images into smaller segments. Yeah.
And very interesting. So kind of like when it's generating paragraphs, it's just like
Mm.
make the token size smaller, shorter.
Yeah, then this is making the embedding size larger. So like maybe 256 or maybe 512.
Okay, okay, okay. So each image cut into smaller chunks, but the embedding larger, meaning that more types of information
Yeah.
get recorded
Yes.
when describing each patch.
Yeah, kind of.
Mhm.
Yeah, you can see it's quite consistent throughout the examples.
Mm.
And basically, this means that more operations actually better quality.
Mm.
And so let's go back. So now we train a second experiment. So we train 12 DIT models as size S, size base, size large, and extra large. So all of them using adaLN normal 0 variant. And patch size, they try 8, 4, and 2. And they try increasing the model size with deeper and wider transformers. So deeper simply means more layers, and the wider means the larger the size of embedding. And they try decreasing patch size, which will result in more floating point operations. The number of parameters remain roughly constant. So what they find that the scaling improved the FID score. So they have so we have the diagram. So because FID lower the better, and so square, the blue dots are actually the XL size, so X, and then you can kind of see that as we have sort of a smaller patch size, we will have a better image quality, like lower FID score, sort of. And typically, smaller patch size will result in more floating point operations. And so now GFlops, basically the floating point operation that actually improve the performance. Because decreasing patch size, the parameters actually stay fixed, number of parameters, and however, the number of floating point operations increases substantially. And they find a negative correlation because lower FID is better. So basically it means that more floating operation will give you higher FID score. I mean lower FID score. And now we can look at the compute efficiency. So typically larger DiT models use training compute more efficiently, and smaller models become inefficient even when training longer. So they found out larger models achieve better FID with fewer total gradient, total floating point operations. So they find that larger models like the XL models produce sharper images than the base model, let's say. And so to summarize, so conditioning actually affects the diffusion quality, and the layer norm 0 achieve the best quality. And the scaling the number of floating operation is the driver of quality, and transformers scale cleanly as the diffusion backbones. And the final evaluation is a bunch of numerical stuff. So we train the largest model with the smallest patch size. We train it with 7 million step, and we evaluate the class conditional generation on the ImageNet dataset. And we compare against the state-of-the-art generative models, and we use the classifier-free guidance during sampling. So let's look at the table. Where's the table? So this is the result table. So the first row we have the GANs and the style GAN. And the second row we have the ADM. ADM basically it's a UNet backbone that uses the pixel space. And then LDM they use the latent space. And then finally the last row is the diffusion transformer stuff. And you can see that typically it has the lowest FID and has the highest inception score. And the precision and recall we'll explain the next slide. And they found out for the 5x12, 512 by 512 image, they also have similar results in which the diffusion transformer achieves the state-of-the-art performance for FID and also for the IS. And for precision and recall, you can see it's quite similar, quite close to the state-of-the-art, and also for recall as well. So what is precision and recall here? So precision here simply means that if we want the generated image to be as realistic as possible, so it should not contain like artifacts. And recall here simply means diversity. So if I want to generate maybe 1,000 images, so you should cover as many classes as possible. So usually the higher the better for these two values. And that's pretty much. So to conclude, the paper introduces the diffusion transformer as a transformer backbone for diffusion models, and it outperforms UNet-based diffusion models, and it scales reliably with the increasing model size, and it inherits the scaling properties of transformers and can serve as a good backbone for even text-to-image models, basically diffusion stuff. So yeah, any questions? That's basically everything for today.
No question from my end. It was very interesting. At the same time, so much like informations.
Yeah.
Hey, Colby, do you know when we get something into latent space, um, Is that representation able to have like an arbitrary amount of channels, or is it going to have three channels? Um, I'm kind of wondering how, like, do you know how we visualize latent space? I'd be curious to see a latent representation.
I think you have arbitrary number of channels. For stable diffusion, they use four channels.
Okay.
Yeah.
Still spatial, right? So you can do patchify and stuff.
Yeah. It's like 32 by 32 by 4 typically.
Oh, there.
Right.
Yeah. Any other questions?
So not to oversimplify, but pretty much it just feels like all the same diffusion stuff, but
Mhm.
instead of a unit, we just took diffusion vision transformer stuff.
Yeah.
That's
Yeah.
pretty much it.
Yeah, it's pretty much, it's not that complex, actually.
Perfect.
Yeah.
Yeah, the transformer is known for its simplicity.
Okay.
Yeah, also saying it's that for is the so the kind of the UNet in here is much less, and the flow matching is not really part of this model.
Flow matching, yeah, this is diffusion. Flow matching, you can also use transformer, I think.
Okay, I'm very curious now to see it's yeah, I wanted to see kind of the latest image generation model. Uh,
Mm,
what do it which perform which architecture is predominant one now?
yeah, we can look into that, definitely. Cool, perfect. That's good.
Okay. All right. Maybe what I'll quickly say is that quickly introduce about our group, but um, and uh, and and we'll also quickly talk a little bit about the next session. Oh, actually, can you allow me to share screen quickly?
Yeah, you can share right now.
Okay, perfect. And then um, let me see. So just wanted to quickly uh, give a little bit of intro to what who we are really. It's that we are a um, behind this paper reading group, it's a AI learning community called AI Scholars, and then also shared as Discord joining link for us. So really, it's a community that's made of friends from uh, mostly based online, but mostly located in New York, SF, Boston, Waterloo area, and then so we are friends that are either researchers or engineers or product builders that are in the diffusion model and transformers space that are really trying to learn the latest uh, advancements in here. And then particularly the paper reading group is something that we are meeting once per month, and it's part of uh, previously 5 months. Now we are thinking about turning it into a 3 months program that we go through the MIT's diffusion model and flow matching course. So they are so it's one of the world's best course on diffusion model, and then they just started and we are going through their 2025 course syllabus and then course notes. They are also starting another one for 2026, and their course notes will be out very soon. And then uh, so we are also thinking about hosting another cohort that actually goes through uh, the newer version, and then uh, uh, and also it will if it is out. So and then what it's actually really does is that really covers the every aspects of the diffusion model and then flow matching model to the latest kind of image generation models architectures. So and then throughout the course, kind of the few really most important thing we are helping all of us to really get. One is to help us to um, kind of understand diffusion model and understanding paper and then implementing few of the paper and then train our own models. And then also is to kind of, as part of paper reading group, kind of catching up with the latest papers and then be able to read latest papers and then understand the latest advancements. And then overall, this is just providing us a learning experience that help us to learn through building and learn through accountability with friends. And then it's uh, so so the monthly paper reading group will be continue organizing, and then it's going to be free for everyone and then to join. And then but the structured class that we are following the MIT's course notes for will be a 3 months kind of structured commitment for us. So that will be paid, and particularly um, the we will be going through this would be like kind of the general format, and then and we will be building a few diffusion model projects from building your own diffusion model to build a full stack app that connecting with the fine-tuned diffusion model with ConfUI with a real client project, and then potentially your own proposed project as well, and then having our mentors and mentors, and then also happy students. And then if you're actually interested in joining our next cohort, it's going to be $100 per month. And then with um, uh, for people who have financial issue can discuss. And then yeah, and then for to answer questions in real life events in NYC, we occasionally have them when I am there, or when if you of you guys wanted to meet up. We do have Alex and then what's the lady's name? Nope, I think forgot. And then also you Alp are in New York. So if you guys wanted to meet up, feel free to meet up. And then oh wow, great. Oh, there's a Coffee UI meetup in New York. Amazing. And then so uh yeah, so love to help you uh meeting together and then connect with each other. Particularly, we are also just starting a paper. So we have a paper reading uh channel here that's we will be uploading our paper reading like events and then the PDF that we went through in here. So for today's PDF, you can find it here. And then actually, if you also want to just join this public paper reading group, it's quite empty, but we have this chat where we are talking about the future sessions. And then you can also follow us on our Luma events link. So that's going to be luma.com/AI scholars, and then to see our future events. And then especially one coming up for the December the 30th, another workshop, and then on our AI agents, which is another course we're teaching. So yeah, and if you are interested in this or wanted to learn more, feel free to message me over this calendar booking link or over LinkedIn or Discord, and we'll be sharing that information as well. And then I also wanted to say for the next week for the we will not have a paper reading group, but also it's going to be the but we will have a but we'll have the kind of the class, and then the class we will be talking we are still just among ourselves, the classmates. The part we are likely be going into is going to be the LoRa fan tuning, and then we potentially I'm thinking about maybe we have the previously trained LoRa fan-tuned model that we can actually walk people through how we actually build it, and then actually we could also potentially be working through the LoRa paper. Kobe, if that's something you think is relevant, if you wanted.
Yeah, so talk about LoRa next week, you mean?
Yeah.
Oh, yeah, I can prepare some slides.
Yeah. And then any other, and also another thing I just wanted to say is that to all of us, we are also organizing a end of the year uh kind of a friends gathering events. So just for I'm just sending you guys this link, which is also the next week Sunday. It's organized by AI scholars and our friends, which is a yearly reflection and friends making workshop. Feel free to join. Yes. That's a send. And any other questions? I think this is the time. Feel free to for us to mingle. We and also for us as an update for our like trained LoRa model. We it's doing well for the very recent model, and so we are in the middle of training another one. And for tracing, I didn't get to train that yesterday, but we'll be doing that today. Yeah, cool.
Perfect.
Yeah. And then so anything and any other things that we wanted to chat about, feel free if you are interested, feel free to stay around. But otherwise, we have finished all the today's topics.